Right now, at this very moment, something extraordinary may exist beneath the frozen, radiation-scorched deserts of Mars. 7 to 12 miles below the surface, deeper than the deepest mines on Earth, deeper than most drilling operations have ever reached, seismic data suggests the presence of liquid water. Not frozen, not vapor, liquid, trapped in fractured rock and extending across regions larger than entire continents. If this interpretation of the seismic readings proves correct, this hidden reservoir contains enough water to cover the entire planet under an ocean more than a mile deep. And on Earth, wherever liquid water exists, even miles beneath the surface, even in the most extreme conditions imaginable, in boiling acidic springs, in frozen Antarctic lakes, in the crushing darkness of the deep ocean floor, life finds a way to survive. The implications are staggering. For decades, we've searched for traces of ancient life on Mars, looking backward in time to when rivers carved through valleys and lakes shimmered under alien skies billions of years ago. But this discovery, announced in August 2024 after years of analyzing seismic data from NASA's InSight lander, suggests we may have been looking in the wrong place. Based on what we know about life's resilience on Earth, we can reasonably assume that if life ever emerged on Mars, it might not be extinct. It might be hiding, right now, in the deep places we haven't yet reached. For thousands of years, humans have looked up at a bright red dot in the night sky and wondered. Ancient civilizations named it for their gods of war. The Romans called it Mars. The Greeks knew it as Ares. The Babylonians named it Nergal, their god of death and pestilence. Modern scientists sent machines across millions of miles to touch its soil. And between those two moments lies a story of discovery so rich, so layered with surprises and contradictions, that even now we're only beginning to read the first chapters. Hello there, and welcome to the Sleepable Science channel. I'm so glad you found your way here. Maybe you've spent your day thinking about distant worlds, or perhaps you're simply looking for something fascinating and calming to help you drift towards sleep. Either way, tonight we're traveling together. Not physically, of course, but in mind and imagination, across the dark gulf of space to visit Earth's enigmatic neighbor. You've got nothing to do but rest. Let your shoulders drop, your breathing slow, and your thoughts settle like dust on an ancient plain. Because tonight, we're going to Mars. Not with rockets or spacesuits, but with curiosity and wonder. We'll walk across towering volcanoes that dwarf anything on Earth, peer into canyons deep enough to swallow mountain ranges, and search for signs of water that flowed billions of years ago. We'll learn about the robots that have crossed its surface, the mysteries of its two strange moons, and the tantalizing hints that life may have once emerged in its ancient seas. Some of what you hear tonight might surprise you. Other discoveries will feel like pieces of a puzzle slowly coming together, revealing a world that was once very different from the frozen desert we see today. If these calm explorations help you unwind or spark your curiosity about the cosmos, consider liking and subscribing to the channel. It helps others find their way here too, one curious mind at a time. Now, let's begin our journey to the Red Planet. The Red Planet's identity. Mars hangs in space at an average distance of 142 million miles from the Sun, positioned as the fourth planet in our solar system. But this number tells only part of the story. Because Mars travels in an elliptical orbit, its distance from the Sun varies significantly throughout its year, ranging from about 128 million miles at its closest approach to 154 million miles at its farthest point. This eccentric path has profound effects on the planet's climate and seasons, creating temperature swings far more dramatic than anything Earth experiences. When we look at Mars through a telescope, we see a world that is distinctly smaller than our own. With a diameter of approximately 4,212 miles, or more precisely, 4,220 miles, 6,701 kilometers, Mars is roughly half the size of Earth. If you could place Earth and Mars side by side, our planet would look like a basketball next to a softball. This difference in size translates directly to mass. Mars contains only about 11% of Earth's mass, weighing in at roughly 601 billion trillion kilograms. This lower mass has cascading effects throughout the Martian system, from its thin atmosphere to its weaker gravitational pull. Standing on the surface of Mars, you would weigh only about 38% of your Earth weight. A person who weighs 150 pounds on Earth would feel like they weighed just 57 pounds on Mars. This reduced gravity profoundly shapes everything about the planet, from how dust settles in the atmosphere to how high volcanoes can grow before their own weight causes them to spread outward rather than climb upward. The planet's distinctive rusty red appearance, visible even to the naked eye from Earth, comes from iron oxide, better known as rust, coating much of its surface. The Martian soil, or regolith as scientists call it, is rich in iron minerals that have been oxidized over billions of years, creating a planet-wide patina of rust. But this red is not uniform. Depending on location, lighting, and the minerals present, Mars displays a surprising palette of colors. Some regions appear golden brown, others tan or greenish, and certain areas even show hints of blue-gray where different minerals dominate the surface. The sky itself, when viewed from the Martian surface, often appears butterscotch or peachy tan, tinted by the fine dust suspended in the thin atmosphere. Beneath this rusty exterior lies a structured interior similar in some ways to Earth's. Mars has a dense metallic core, likely composed of iron, nickel, and sulfur, with a radius somewhere between 930 and 1,300 miles. This core is surrounded by a rocky mantle extending upward for hundreds of miles, and above that lies a crust averaging between 26 and 35 miles thick. In some places, particularly in the Isidis Planitia basin, the crust thins to as little as 4 miles, while in other regions it swells to more than 70 miles deep. One of Mars' most intriguing features becomes apparent when you examine its two hemispheres. The southern hemisphere is heavily cratered, ancient, and sits at a higher elevation, a rugged landscape bearing the scars of billions of years of asteroid impacts. The northern hemisphere, by contrast, is remarkably smooth, consisting of vast lowland plains that lie several miles below the southern highlands. This stark difference, known as the Martian dichotomy, has puzzled scientists for decades. One hypothesis that has been explored to explain this dramatic divide suggests this could have resulted from a colossal impact early in Mars' history. This interpretation proposes that a Pluto-sized body struck the northern hemisphere and reshaped a third of the planet's surface. If this proves correct, the impact basin would be one of the largest in the solar system, spanning roughly the combined area of Europe, Asia, and Australia. However, it's important to note that the evidence for this giant impact hypothesis remains inconclusive. Alternative explanations involving internal geological processes, such as mantle convection patterns or early crustal formation variations, continue to be explored and debated within the scientific community. The mystery of what caused this hemispheric divide remains one of Mars' most compelling unsolved questions. A Martian day, called a sol, lasts 24 hours, 37 minutes, and 22 seconds, remarkably similar to Earth's 24-hour day. This similarity is one of the many coincidences that make Mars feel somehow familiar despite its alien nature. But a Martian year stretches to 687 Earth days, nearly twice as long as our own. Mars takes longer to complete its orbit because it lies farther from the Sun and must travel a greater distance around it. Like Earth, Mars has an axial tilt, the angle at which its rotation axis leans relative to its orbital plane. Mars tilts at about 25.2 degrees, very close to Earth's 23.4-degree tilt. This similarity means Mars experiences seasons much like we do, with summers, winters, springs, and falls in both hemispheres. However, because of Mars' eccentric orbit, these seasons are far from equal. Southern summer occurs when Mars is closest to the Sun, making it shorter but more intense, while northern summer happens when Mars is farthest from the Sun, creating milder but longer warm periods. These seasonal extremes drive powerful weather patterns across the planet, including the massive dust storms that can occasionally engulf the entire world. When we measure Mars against our own planet, we find it has about 28% of Earth's surface area. This might sound small, but there's an interesting comparison worth noting. While Mars has just over a quarter of our planet's total surface area, it actually has about the same amount of dry land as Earth. Because 71% of Earth's surface is covered by oceans, the land area of Mars roughly equals all of Earth's continents and islands combined. In a sense, Mars offers just as much solid ground to explore as our home world, though its landscapes present very different challenges and mysteries. A world of extremes, temperature on Mars varies wildly, far more than the seasonal shifts we experience on Earth. At the equator during summer, afternoon temperatures can climb to a relatively pleasant 70 degrees Fahrenheit, 20 degrees Celsius, but as night falls, temperatures plummet to well below freezing. Near the poles during winter, thermometers would register readings as low as negative 195 degrees Fahrenheit, negative 125 degrees Celsius. This dramatic temperature swing, over 260 degrees Fahrenheit in some cases, results from the planet's thin atmosphere, which cannot retain heat the way Earth's atmosphere does. The atmosphere itself is incredibly tenuous. Standing on the surface of Mars, you would experience atmospheric pressure less than 1% of what you feel at sea level on Earth, specifically about 600 pascals compared to Earth's 1300 pascals. This is roughly equivalent to standing at an altitude of 100,000 feet on Earth, far above the height where commercial jets fly. At such low pressure, liquid water cannot exist for long. It either freezes solid or evaporates directly into vapor, never remaining in the liquid state that life as we know it requires. This thin atmosphere consists almost entirely of carbon dioxide, about 96%, with small amounts of nitrogen, 1.93%, and argon, 1.89%, plus traces of oxygen, water vapor, and other gases. While carbon dioxide is a greenhouse gas that traps heat, there's simply not enough atmosphere on Mars to create a significant warming effect. The planet cannot hold on to the sun's warmth, and each night sees temperatures drop precipitously. The atmospheric thinness also means Mars offers little protection from solar radiation. On Earth, our thick atmosphere and magnetic field shield us from the sun's most harmful rays. Mars, however, lost its global magnetic field billions of years ago when its interior cooled and its dynamo shut down. Without this protective shield, and with only the thinnest veil of atmosphere, the surface is bathed in radiation that would be lethal to unprotected humans and damaging to most forms of life we know. And yet, this thin atmosphere moves with surprising vigor. Martian winds can reach speeds of 60 miles per hour or more, and during spring and summer in the southern hemisphere, they sometimes trigger dust storms that grow to cover the entire planet. These global dust storms can last for months, turning day into twilight and dropping temperatures across the world as sunlight is blocked. The dust itself is incredibly fine, with particles averaging just 1.5 micrometers in diameter, about 50 times smaller than a human hair. This dust gives the Martian sky its characteristic butterscotch hue and coats everything on the surface with a rusty powder. Mountains and canyons beyond imagination. Mars is home to geological features that dwarf anything on Earth. Olympus Mons, the largest known volcano in the solar system, rises approximately 13.6 miles, 22 kilometers, above the surrounding plains, about 2.5 times the height of Mount Everest above sea level. But height tells only part of the story. Olympus Mons is so massive that it stretches about 370 to 400 miles, 600 to 650 kilometers, across, roughly the size of the entire state of Arizona, or comparable to France. The volcano's summit features a complex caldera, a collapsed crater, measuring about 50 miles, 80 kilometers, wide, formed by multiple overlapping collapse events as magma chambers emptied beneath the surface. Around the volcano's base runs a cliff, or escarpment, that rises as high as 6 miles, 10 kilometers in places. This cliff's origin remains a subject of scientific debate. Some researchers suggest it formed from massive landslides, while recent studies propose it could indicate that the volcano once stood as an island in an ancient Martian ocean, with waves eroding its base. Despite its enormous height, Olympus Mons has remarkably gentle slopes, averaging only about 5%. This shallow angle means that if you stood at its base, the summit would lie beyond the horizon. And if you somehow climbed to the top, you wouldn't feel like you were standing on a mountain. The slope would extend in all directions beyond your view. You would, however, notice something extraordinary. At the summit, the atmospheric pressure drops to only about 72 pascals, roughly 12% of Mars' already thin average surface pressure. The peak literally pokes through a significant portion of the atmosphere. The evidence suggests Olympus Mons is geologically young, at least by planetary standards. While the volcano itself formed over billions of years, some of its surface features and lava flows appear to be only a few million years old. This implies the volcano was active in the relatively recent past and could, in theory, erupt again, though it has shown no signs of activity throughout the space age. The size of Olympus Mons, and indeed all of Mars' giant volcanoes, owes much to the planet's lack of plate tectonics. On Earth, volcanic hotspots create chains of islands like Hawaii because the crust constantly moves over the stationary plume of rising magma. The hotspot builds a volcano, the crust shifts, and the hotspot begins building a new volcano in a different location. On Mars, the crust doesn't move. A hotspot can continue feeding the same volcano for billions of years, allowing it to grow to sizes impossible on Earth. Not far from Olympus Mons stretches another of Mars's superlatives, Valles Marineris, a system of canyons so vast it makes Earth's Grand Canyon look like a modest crack. This enormous gash in the planet's surface extends about 2,500 miles, 4,000 kilometers, from east to west, roughly the width of the United States from coast to coast. In places, the canyon system reaches depths of up to 4.3 miles, 7 kilometers, with sections widening to 200 miles, 320 kilometers, across. To give perspective, Earth's Grand Canyon is about 277 miles long, 18 miles wide at its broadest point, and just over a mile deep. The formation of Valles Marineris remains something of a mystery, though geological evidence points to several processes working together. Unlike Earth's Grand Canyon, which was carved by the Colorado River over millions of years, Valles Marineris appears to have formed primarily through tectonic forces, specifically the stretching and cracking of Mars' crust as the nearby Tharsis volcanic bulge rose billions of years ago. Some sections show evidence of later modification by water erosion, suggesting that at some point in Mars' past, water may have flowed through parts of the canyon system. The canyon's walls display distinct layering, revealing billions of years of Martian geological history. These layers contain minerals that formed in the presence of water, including sulfates and clays, suggesting that Mars was once much wetter than it is today. Landslides have carved massive scars down some canyon walls, with debris fields spreading for hundreds of kilometers across the canyon floor. Some of these landslides involve volumes of material measured in cubic kilometers, among the largest mass movements ever identified on any planet. Water's hidden story. Perhaps no question about Mars has captured more attention than this. Where did the water go? Evidence for ancient water on Mars is overwhelming and comes in many forms. Orbital images reveal dried river channels, deltas where rivers once emptied into lakes, and basin floors that show the unmistakable signs of standing water. Rovers have photographed rounded pebbles, stones that could only have been shaped by tumbling in flowing water. The Mars Science Laboratory's Curiosity rover found sedimentary rocks in Gale Crater that clearly formed in an ancient lake bed, complete with mud cracks that had dried under an ancient sun. Chemical analysis has revealed minerals that only form in liquid water. Clay minerals, sulfate deposits, and various hydrated minerals dot the Martian surface, locked into rocks that formed billions of years ago. Some of these minerals require not just water, but water of specific chemical compositions, neutral pH in some cases, acidic conditions in others, painting a picture of diverse aqueous environments. Current estimates suggest that ancient Mars held enough water to cover its entire surface to a depth of at least 450 feet, 137 meters, though this water was never spread uniformly. Based on the geological evidence, we can reasonably infer it collected in lakes, flowed through river valleys, and possibly pooled in a vast northern ocean. The question that has puzzled scientists for decades is simple, yet profound. Where did all that water go? Three main fates have been proposed, and the evidence suggests all three played roles. First, some water escaped into space. Without a global magnetic field to protect it, Mars's atmosphere was gradually stripped away by the solar wind, a stream of charged particles from the sun. As the atmosphere thinned, water vapor in the atmosphere was broken apart by solar radiation. The hydrogen, being light, could then escape Mars's weak gravity and drift off into space. Measurements from Mars orbiters have directly observed this process continuing today, though at a much slower rate than in the distant past. Second, much water froze and remains frozen on Mars today. The polar ice caps contain substantial reserves of water ice, overlain with seasonal caps of frozen carbon dioxide, dry ice. But ice isn't confined to the poles. Ground-penetrating radar on orbiting spacecraft has detected vast sheets of ice buried beneath dust at mid-latitudes, sometimes more than 300 feet, 100 meters, thick. Impact craters occasionally expose brilliant white ice that had been hidden just beneath the surface. The evidence suggests that enormous amounts of water remain frozen on or just beneath Mars' surface. And third, water may have soaked into the ground and remains there, locked in the crust, which brings us to one of the most exciting recent discoveries about Mars. The data comes from NASA's InSight lander, which operated on the Martian surface from 2022. Among InSight's instruments was a highly sensitive seismometer called SES, Seismic Experiment for Interior Structure, which detected more than 1,300 Marsquakes during its mission, the first seismic activity ever recorded on another planet. When a Marsquake occurs, it sends seismic waves traveling through the planet's interior. Different types of waves travel at different speeds, depending on what materials they pass through. By analyzing the velocity of these waves, scientists can infer the properties of Mars's interior layers, much as geologists use earthquake waves to map Earth's internal structure. In August 2024, a team of geophysicists published their analysis of InSight's seismic data in the Proceedings of the National Academy of Sciences. The researchers, Vashon Wright of the University of California, San Diego's Scripps Institution of Oceanography, Matthias Mortzfeld, also of Scripps, and Michael Manga of the University of California, Berkeley, reported something remarkable. The seismic data from Mars' mid-crust at depths between 7 and 12 miles, 11.5 and 20 kilometers, suggests the presence of liquid water. Specifically, the velocities of seismic downed waves passing through this region are consistent with a model where fractured igneous rocks are saturated with liquid water. The data shows that both P waves, compressional waves that travel fastest, and S waves, shear waves that move more slowly, behave in ways that align with what we would expect if the rocks at those depths were filled with liquid in their pores and fractures. To test their hypothesis, the researchers performed laboratory experiments using diabase rock from Sweden, which serves as one of the best terrestrial analogues to Martian rock. When these diabase samples were saturated with water, they produced seismic signatures remarkably similar to what InSight's seismometer detected on Mars. If this interpretation is correct, and it's important to note that this conclusion is based on indirect measurements and modeling, so additional confirmation would strengthen confidence. The implications are staggering. The researchers estimate that if the region beneath the InSight lander is representative of the rest of Mars, there could be enough groundwater in the mid-crust to cover the entire planet to a depth of 1 to 2 kilometers, 0.6 to 1.2 miles. That's more water than the volumes proposed for Mars' hypothesized ancient oceans. This finding, if confirmed, would help solve a major mystery. It suggests that much of Mars' ancient surface water didn't escape to space or freeze in ice caps. Instead, it filtered down into the crust, where it remains today in liquid form, protected from the harsh surface conditions by miles of overlying rock. There is, however, a significant challenge. This water, if it exists, lies far deeper than any current or planned Mars mission could reach. Even on Earth, drilling to depths of 7 to 12 miles represents an extreme technical challenge. On Mars, with its thin atmosphere, extreme cold, and the need to transport all equipment across millions of miles of space, accessing this deep groundwater would require technological capabilities far beyond what we currently possess. Yet for scientists seeking evidence of life on Mars, this discovery, if verified, points to a promising place to look. On Earth, what we know is where it is wet enough, and there are enough sources of energy, there is microbial life very deep in Earth's subsurface, Wright noted in the study's announcement. The ingredients for life as we know it, liquid water, organic compounds, and sources of energy, could exist in Mars' mid-crust. The challenge is reaching them. The mystery of Mars' two moons. Mars has two small, irregularly shaped moons. Phobos and Deimos, discovered in 1877 by American astronomer Asaph Hall using a 26-inch telescope at the U.S. Naval Observatory. They're named after the sons of Ares, the Greek counterpart of Mars, who served as his chariot drivers in mythology. Phobos means fear, and Deimos means panic, fitting companions for the god of war. These moons are tiny compared to Earth's moon. Phobos, the larger of the two, measures about 17 miles, 27 kilometers, across at its widest point. Deimos is even smaller, at roughly 9 miles, 14 kilometers in diameter. Both are irregularly shaped, lumpy bodies that lack the gravitational pull necessary to compress themselves into spheres. They look more like captured asteroids than traditional moons, and for decades, that's exactly what many scientists believed they were. Asteroid belt objects gravitationally captured by Mars long ago. However, recent research suggests a more complex origin story. Studies of the moon's orbits, compositions, and physical characteristics have raised questions about the capture hypothesis. For one thing, both moons orbit Mars in nearly circular equatorial orbits, exactly the orbits you would expect if they formed alongside Mars rather than being captured from elsewhere. Captured objects typically follow more elliptical, tilted orbits. An alternative theory proposes that Phobos and Deimos formed from debris flung into orbit around Mars by a giant impact billions of years ago. This interpretation suggests a massive collision could have ejected material that later coalesced into the two moons, similar to how some scientists believe Earth's moon formed. Recent computer models support this scenario, though the question remains open for debate. Phobos orbits exceptionally close to Mars, only about 3,700 miles, 6,000 kilometers above the surface. To put this in perspective, Earth's moon orbits at an average distance of about 240,000 miles. Phobos is so close that it orbits Mars 3 times every Martian day, rising in the west and setting in the east just 4.5 hours later. Tidal forces from Mars are gradually pulling Phobos closer, lowering its orbit by about 6 feet, 1.8 meters, every century. Current calculations suggest that in about 50 million years, Phobos will either crash into Mars or be torn apart by tidal forces, forming a ring system around the planet. Deimos orbits farther out at about 14,500 miles, 23,000 kilometers, and takes slightly more than a Martian day to complete one orbit. From the surface of Mars, Deimos would appear about as bright as Venus appears from Earth, a very bright star, but not obviously moon-like. Both moons are heavily cratered, bearing the scars of billions of years of impacts. Phobos features a particularly prominent crater named Stickney, about 5.6 miles, 9 kilometers across, nearly half the moon's diameter. The impact that created Stickney must have nearly shattered Phobos completely. Grooves and linear features on Phobos's surface may be fractures from this impact, or possibly tracks left by boulders rolling across the surface after being ejected during the collision. Mars through time, a planet's evolution. To understand Mars as it is today, we must look back across more than 4.5 billion years of history. Mars formed during the early solar system's chaotic adolescence, condensing from the disk of gas and dust that surrounded the young sun. At first, it was a ball of molten rock, heated by countless impacts and the decay of radioactive elements. Gradually, the surface cooled enough for a crust to form, preserving in its oldest rocks a record of those earliest times. During the first half-billion years of its existence, a period geologists call the Noachian, named after Noachis Terra, an ancient heavily cratered region, Mars was a dramatically different world. The evidence carved into its rocks and surface tells a story of abundant water. This was the era when rivers flowed through valleys, when lakes filled crater basins, and when, based on what geological features suggest, a vast ocean may have covered much of the northern lowlands. What made this wet climate possible? Mars must have had a much thicker atmosphere than it possesses today, perhaps with sufficient greenhouse gases to trap enough heat to keep surface temperatures above freezing for extended periods. The planet may still have had an active global magnetic field at this time, generated by convection in its molten core, which would have helped protect the atmosphere from erosion by the solar wind. But Mars is smaller than Earth, and smaller planets cool faster. As Mars's interior gradually cooled over hundreds of millions of years, its magnetic dynamo sputtered and died. Without the protective shield of a global magnetic field, the solar wind began stripping away the atmosphere. This process wasn't instantaneous. It unfolded over hundreds of millions of years, but the effect was cumulative and ultimately catastrophic for any life that may have emerged on the surface. As the atmosphere thinned, Mars's ability to retain heat diminished. Surface temperatures dropped. Water began to freeze. The wet climate that had characterized the Noachian period gave way to a drier, colder world during the subsequent Hesperian period, roughly 3.7 to 3 billion years ago. Volcanic activity continued. Tharsis was still growing. Olympus Mons was rising. But the surface environment was growing increasingly hostile to liquid water. By the time the Amazonian period began about 3 billion years ago and continues to the present, Mars had become the cold, dry desert we observe today. The transformation from a potentially habitable world to a frozen wasteland represents one of the most dramatic climate changes we know of in the solar system. This history raises profound questions. If Mars was once warm and wet, and if liquid water persisted on its surface for hundreds of millions of years or more, did life emerge there? On Earth, life appeared remarkably quickly once conditions allowed it. Evidence of life appears in rocks dated to within a few 100 million years of Earth's formation. If the same process occurred on Mars, then fossils of ancient Martian organisms might still exist, preserved in the rocks that formed during the Noachian period. And if life did emerge during that early wet period, could some forms have survived the transition to the harsh modern climate by retreating underground into protected subsurface environments where liquid water might still exist? The discovery of potential deep groundwater makes this possibility seem less far-fetched than it once did. A century of exploration, humans have been sending spacecraft to Mars since the dawn of the space age, and the history of these missions is marked by both triumph and heartbreak. The Soviet Union made the first attempts in the early 1960s, but technical failures doomed those early missions. Mars 1, launched in 1962, lost contact before reaching the planet. NASA's first attempts faced similar challenges. Mariner 3's shroud failed to separate, sending it tumbling uselessly through space. But persistence paid off. In 1965, Mariner 4 became the first spacecraft to successfully fly past Mars, sending back 22 images that revealed a cratered, moon-like surface. These first glimpses disappointed many who had hoped to see a more Earth-like world, but they marked the beginning of systematic Mars exploration. The pace accelerated through the 1970s. NASA's Mariner 9, arriving in 1971, became the first spacecraft to orbit another planet and revealed a Mars far more complex and interesting than Mariner 4 had suggested. A world with giant volcanoes, vast canyons, and evidence of ancient water. Then came the two Viking missions in 1976, each consisting of an orbiter and a lander. The Viking landers touched down on Mars' surface and operated for years, sending back the first photographs from the Martian surface and conducting the first experiments explicitly designed to search for life. The Viking biology experiments produced tantalizing, ambiguous results that scientists still debate today. None provided definitive evidence for life, but some results defied easy explanation in purely chemical terms. The debate over their interpretation helped shape subsequent Mars exploration strategy. Rather than searching directly for life, future missions would search for evidence of habitable environments and biosignatures, chemical or physical evidence that life once existed. After Viking, a long gap followed. Mars missions in the late 1980s and 1990s suffered from technical failures and budget constraints. The loss of Mars Observer in 1993, just before it was to enter orbit, was particularly devastating. The failure of Mars Polar Lander and Mars Climate Orbiter in 1999, the latter due to a simple unit conversion error between metric and imperial measurements, led NASA to re-evaluate its approach. But the new millennium brought renewed success. Mars Pathfinder, which landed in 1997, deployed Sojourner, the the first wheeled rover on Mars, demonstrating that mobile platforms could survive and operate on the surface. The Mars Global Surveyor Orbiter, operating from 1997 to 2006, mapped the planet in unprecedented detail, revealing layers in the polar ice caps, gullies that might have been carved by recent water flows, and countless other features. Then came the Mars exploration rovers Spirit and Opportunity, landing in January 2004 in locations chosen specifically for their potential to preserve evidence of past water. Both were designed to operate for 90 Martian days. Spirit lasted more than 6 years, Opportunity for nearly 15, a remarkable testament to robust engineering and a bit of luck. The Martian winds occasionally cleaned dust from their solar panels, extending their lives far beyond expectations. Opportunity's discoveries transformed our understanding of Mars. The rover found hematite blueberries, small spherical concretions that form in water, scattered across the surface of Meridiani Planum. It drove through ancient crater basins whose rocks contained minerals that only form in liquid water. It examined layers of sedimentary rock that told stories of ancient lakes and changing water chemistry. By the time Opportunity finally fell silent during a global dust storm in 2018, it had traveled 28 miles, 45 kilometers, and revolutionized our understanding of Mars' watery past. While the rovers explored the surface, orbiters continued studying Mars from above. Mars Reconnaissance Orbiter, arriving in 2006 and still operating today, carries the most powerful camera ever sent to another planet, capable of resolving features as small as a few feet across. It discovered evidence of recurring slope lineae, dark streaks that appear seasonally on some slopes and might represent briny water flows. It mapped the location of subsurface ice across the planet. It monitored weather patterns and watched dust storms develop and evolve. In 2012, NASA landed its largest and most capable rover yet. Curiosity, the centerpiece of the Mars Science Laboratory mission. The size of a small car and powered by a radioisotope thermoelectric generator rather than solar panels, Curiosity was designed to determine whether Mars ever had conditions suitable for life. It landed in Gale Crater, chosen because the crater contains a 5-mile-high mountain of layered sediments that could preserve a record of Mars' changing climate. Curiosity's discoveries have been profound. In its first few months, it found rounded pebbles, clear evidence of an ancient stream bed. It identified clay minerals that form in neutral pH water, favorable for life. It detected organic molecules, carbon-based compounds that are the building blocks of life as we know it, in rocks dated to 3 billion years old. It found evidence that Gale Crater once held a long-lived lake that may have persisted for millions of years, a place where, in principle, life could have thrived. The findings from Curiosity definitively established what scientists had begun to suspect. Ancient Mars was habitable. It had liquid water, neutral pH conditions, energy sources, and organic molecules. Whether life actually emerged in these favorable conditions remains unknown, but the prerequisites were there. February 2021, NASA landed Perseverance, the most sophisticated Mars rover ever built. Touching down in Jezero Crater, an ancient lakebed with a beautifully preserved river delta, Perseverance carries an array of instruments designed to search for biosignatures, chemical, textural, or mineralogical evidence that life once existed on Mars. One of its instruments can identify organic molecules and determine their distribution within rock samples with unprecedented precision. Another can analyze the chemical composition of rocks in incredible detail. But Perseverance's most important capability might be the least glamorous. It's collecting rock cores and sealing them in tubes, which it deposits in carefully documented locations on the surface. The vision is that a future mission, a collaboration between NASA and the European Space Agency, would retrieve these samples and return them to Earth. In terrestrial laboratories equipped with sophisticated instruments far too large to send to Mars, scientists could analyze these rocks with a level of detail impossible on the planet itself. Perseverance also carries a technological demonstration that turned into a remarkable achievement: Ingenuity, a small helicopter designed to test whether powered flight is possible in Mars' thin atmosphere. On April 19, 2021, Ingenuity made the first powered, controlled flight on another planet, a Wright brothers moment for the space age. Since then, it has flown more than 70 times, scouting terrain, serving as a pathfinder for the rover, and demonstrating capabilities that will inform future Mars mission designs. Not all recent Mars missions have been American. The United Arab Emirates Hope orbiter, arriving in 2021, focuses on studying Mars' atmosphere and weather patterns from a unique orbit that allows it to observe the entire planet every 9 days. China's Tianwen-1 mission, also arriving in 2021, successfully placed a rover named Zhurong on the surface, making China the second nation to operate a rover on Mars. Zhurong explored its landing site in Utopia Planitia for several months before contact was lost in 2022, though efforts to re-establish communication continue. Looking ahead, plans for Mars exploration remain ambitious despite technical and budgetary challenges. NASA and ESA continue discussing Mars sample return missions that would retrieve the samples collected by Perseverance. Though the exact mission architecture is being reconsidered due to cost and complexity concerns, the scientific value of analyzing actual Mars rocks in terrestrial laboratories is so high that some form of sample return remains a priority. Future rovers might drill deeper than current technology allows, accessing subsurface environments where ancient or even current life might be better preserved. Aerial vehicles like Ingenuity could evolve into larger, more capable drones or balloons, exploring regions inaccessible to wheeled rovers. Some mission concepts envision submarines exploring potential subsurface ice-covered lakes, or drilling rigs boring miles beneath the surface to search for deep biospheres. And beyond robotic exploration, there's the long-held dream of sending humans to Mars. Multiple space agencies and private companies have announced intentions to launch crewed missions to Mars, perhaps as soon as the 2030s or 2040s, though these timelines remain aspirational. These missions face enormous challenges. The months-long transit through deep space exposes astronauts to cosmic radiation and microgravity effects on the human body. Landing heavy payloads intact on Mars strains current technology. Life support systems must function reliably for years with no possibility of resupply from Earth. And perhaps most daunting, astronauts must somehow return safely across millions of miles of space. Yet despite these challenges, the vision persists. Humans walking on Mars, conducting science no robot could match, searching for life with their own eyes and hands, and perhaps eventually establishing permanent settlements. Whether that future unfolds as imagined or takes unexpected turns, our relationship with Mars continues to evolve, from a red dot in the ancient sky to a world we explore with sophisticated robots to, perhaps, a place where humans will one day live and work. Closing, the mirror in the sky. And now, as our journey across Mars draws to a close, there's one final truth worth contemplating, one that quietly emerged as we traced our path from ancient volcanoes to hidden oceans, from dust storms to the search for life. Throughout this exploration, we've learned what Mars was and what it might have been. A world with flowing rivers, standing lakes, perhaps even life in its ancient waters. A planet that, billions of years ago, may have been far more Earth-like than the frozen desert we see today. We've marveled at how different Mars is from our world, how its thin atmosphere couldn't protect it, how its water vanished or retreated underground, how it transformed from a potentially habitable planet into a hostile, radiation-scorched wasteland. But here's the insight that reframes everything we've discussed. Mars isn't showing us an alien world. It's showing us a possible future. The atmospheric loss that stripped Mars bare didn't happen because of some unique Martian weakness. It happened because Mars is smaller than Earth, with weaker gravity and a cooling interior that allowed its protective magnetic field to fade away. Earth has a magnetic field too, generated by our planet's churning liquid outer core. But that core won't stay liquid forever. Billions of years from now, granted far in the future, Earth's interior will cool, our magnetic field will weaken, and the solar wind that stripped Mars' atmosphere will begin working on ours. The process will be slow, measured on geological timescales, but the physics is the same. The climate transformation that reshaped Mars from a warm, wet world to a frozen desert isn't just ancient history. It's a preview. Every greenhouse gas we add to our own atmosphere, every degree of warming we trigger, reminds us that planetary climates are more fragile than they appear. The conditions supporting life can shift, transform, and change on timescales that feel long to us, but are mere moments in a planet's life. Mars shows us what happens when a planet crosses certain thresholds. When atmospheric pressure drops too low for liquid water to persist on the surface, when temperatures plummet beyond recovery, when the balance tips irreversibly toward cold and desolation. When we send rovers to search for fossils of ancient Martian microbes, we're not just satisfying curiosity about whether we're alone in the universe. We're investigating what happens when a life-bearing planet loses its habitability. We're learning to read the geological record of decline, to understand the transitions between living worlds and dead ones. Every dried riverbed, every mineral that formed in the presence of water, every organic molecule locked in ancient stone, tells us something about the boundaries between habitable and hostile, between thriving and extinct. And perhaps most hauntingly, when researchers report evidence that Mars might still harbor deep subsurface water, that life might persist in hidden refuges miles beneath the frozen surface, we're seeing what survival could look like on a dying world. If Martian microbes exist today, clinging to existence in the deep places beyond our reach, they represent what becomes of surface life when a planet's climate collapses irreversibly. They show us where life retreats when the atmosphere fails and the oceans freeze. Into the dark, into the deep, into whatever sheltered environments remain. This is why Mars matters to us, not simply because it's a curiosity or a destination or even a potential second home. Mars matters because it's a lesson written at planetary scale, a 4.5 billion year cautionary tale about what happens when the delicate systems that make a world habitable tip too far in the wrong direction, when protective shields fail, when atmospheres thin beyond recovery. We explore Mars to understand Mars, certainly, but we also explore it to understand Earth, to recognize that our blue world, with its breathable atmosphere and its vast oceans and its teeming abundance of life, isn't the universe's default state. It's an achievement maintained by complex, interconnected systems that have kept conditions stable for billions of years, but aren't guaranteed to last forever without our careful stewardship. When you look at photographs from Mars, those rusty deserts beneath the butterscotch sky, the dried riverbeds and ancient lakebeds, the towering volcanoes standing silent and cold, you're not looking at an alien world. You're looking at a planetary archive, a geological record of transformation. You're seeing what happens when a planet loses its grip on the conditions that allow life to flourish on its surface. And you're being reminded that the world we have, the one we take for granted every day, exists in a state of dynamic equilibrium that requires both cosmic luck and, increasingly, wise planetary stewardship. So tonight, as you rest, perhaps you'll think differently about that red dot in the sky, not merely as a distant curiosity, but as a mirror reflecting possibilities both ancient and future, not just as a place of exploration, but as a place of learning, not simply as Mars, the red planet, but as Mars the archive, Mars the warning, Mars the reminder. Every rock sample we analyze, every crater we photograph, every subsurface ocean we discover through seismic data tells us something about planetary evolution, how worlds begin, how they sustain life, and how they can lose that precious capacity. And in those lessons lies wisdom we desperately need as we face our own planet's uncertain future, as we grapple with our role as the first species capable of significantly altering the climate of an entire world. The story of Mars is, in some ways, a story of loss. The loss of atmosphere, the loss of water, the loss of warmth, and quite possibly the loss of life. But it's also a story of persistence. Water that retreated underground rather than vanishing entirely, minerals that preserved chemical memories of better days, and possibly life that adapted and survived in the one place it could, beneath the surface, beyond our easy reach. Thank you for joining me on this journey to our neighboring world. If these explorations sparked something in you, if they changed how you see Mars or Earth, or the delicate balance that separates living worlds from dead ones, consider subscribing to the Sleepy Science channel. There are more mysteries to uncover, more lessons to heed, and more wonders to discover in the quiet spaces between the stars and in the rocks beneath our feet. Sleep well, and may your dreams carry you to distant worlds and back home again, to the blue marble we call Earth, the most precious thing we know in all the universe, made more precious still by the knowledge that habitability is not guaranteed, that planetary climates can fail, and that the warm, living world we call home is a gift that deserves our deepest care and protection. Good night.